All right, so this is interesting. Check it out. Check it out. Okay, look, so when you superimpose these two, by superimpose I mean lay them down on top of each other. The reds match up, the blues match up, right? The greens and the whites match up. Everybody convinced?
Yes.
All right, now, this one, the red and the white matches up, but look, we can't get the blue and the green to match up. All right, start over. Let's get the blue and the green to match up. Okay, blue and the green, got it. Okay, I got it, look. Oh, but wait. So it looks like no matter what I do with this pair, I can't get them to match up, aka superimpose. So what does that tell us then?
They're different.
They're different. They're different. You wouldn't know from looking at the Lewis structure, because the Lewis structure is not in 3D, right? This is 3D. This is closer to reality than that is. They're both models, but this is closer to reality. Yeah? So you can't tell from looking at the Lewis structure. This is the cool thing about this. You have to build a model, and what we learn from the model is there are two different ways of arranging these four atoms around that tetrahedral carbon.
Only two?
Only two. Only two. Because if I were to take this and this off and switch them, I'd end up back to the same one. Isn't that cool? Okay. So, hang on to the... Now, I kind of rigged that, but I kind of didn't, right? I figured if I got everybody in the class to build a model, there's going to be a pair that will not superimpose, and there will probably also be a pair that will superimpose. Now, if that ever doesn't work out, then we're going to publish a paper. Yeah. Okay, so let's explore this. This is supposed to represent a mirror. Okay? So it's like this molecule is looking at itself in the mirror. So Michaela, come on up here.
Mine doesn't work like that.
If yours doesn't match up with this one, then yours is going to match up with the other one. Hold that one for me with the green. Exactly. Okay. So now I'm looking at myself in the mirror, right? Or this model is looking at itself in the mirror. Right? I look like that. How much would I freak out if I woke up one morning, rubbed the sleep out of my eyes, and went in the restroom and looked at the mirror and I saw someone who didn't look like me? That's a good. I'm sure there's like some sort of horror movie. Not to say that you're Okay, so in the mirror now, look, the blue is across from the blue, right? And the white is across from the white. Yeah, and then the green is far from the mirror. It's away from the mirror, and it's away from the mirror up there. Okay, stay where you are. I need someone else to play Michaela's mirror image. Who wants to come on up here? Come on. Michaela's head is going to be this. Okay? So her head is red. Now put one foot back, Michaela. Like that? Yeah. And her foot is going to represent this. That's the green, okay? So red and green. Okay. Now, this hand is blue. Right. Hold that. Okay, what about this hand? Okay, hold that. Okay. I know, I wish I had a
water bottle.
I'm not going to put my water bottle on it. Okay, now in the reflection, so face, and put your one foot back. Okay. This hand is blue, right? And do you notice it's Audrey's left hand, but it's Michaela's right hand? Okay, and then here, take this. Okay, so now Michaela's looking at herself in the mirror. If she waves her left hand, Audrey actually waves her right hand, right? Okay. Off. Okay. If she waves her right hand, Audrey waves her left hand, right? Good. Now, thank you. So these are called enantiomers. Enantiomers are non-superimposable. They don't match up exactly in space. Mirror images. And there are actual molecules that are like that. This is just one example of a molecule. This example is not that exciting because we don't really do anything with this one. But let me give you another one. Go ahead and take the cap off of that and smell it. Don't say anything. Just think to yourself, what's the first thing that you think of when you smell it? Maybe it's something you've eaten or in a restaurant or Something like that. Don't tell anybody. Just think, what's the first thing that comes to mind, and just keep that in your head. This one, R carbone is spearmint. This one, S carbone is caraway. Do you know what caraway seeds are?
Yes.
The caraway seeds are those brown seeds in the rye bread. That's this one. Alright, so here's this one. Now can you follow this? So the gray is the double bond. Okay? So here's that gray. C double bond into O. Yeah? Yeah. And then down at the bottom of the ring, this carbon right here is this carbon right here. What does dash mean? It's going back. Here's that hydrogen I've marked it. White. And then this group with the double bond is up front. So this one is the S carbone. So we'll leave that one right here.
I know.
Not S-cargo. Now, if you take my organic class, I'll teach you why one is called R and the other is called S. There's like a whole method to that madness.
You guys should take it. It's going to be a party.
It is. It is. Here is the R carbone. Here's that oxygen. And then keep your eye on this carbon, hydrogen going back, and this double bond, this alkene coming up. Right? All right, now I'm going to compare them to each other. What do you notice? Mirror images. The mirror's in the middle. That oxygen, the red, you see reflected across the mirror, right? Now, this white that I'm pointing at over here, that is like when our models up here, our human models, put their foot back, right? Okay. And then here's that white over here. Okay. So if they, yeah, go ahead, Christy.
It seems like the bottom of the one in your left hand isn't like coming out.
Isn't like quite, yeah. You can have free rotation around this single bond. So that actually is rotating in space all the time. So they're mirror images. Okay, so let's try superimposing them. Does it work?
No.
It's really close. So if you focus on that carbon down here, the carbon's attached to four things. One side of the ring and the other side of the ring, which do superimpose, but then this part doesn't, right?
So that makes it smell different?
That makes it smell different. Did I blow your mind?
Yes.
Did I just blow your mind? I told you, did I tell you I was going to blow your mind? So, this is the coolest thing. So there are receptors in your nose that are able to detect that small difference between these two molecules, except for that small percentage of the population.
Yeah, because the difference is so small.
Because the difference is so small, right? So these two interact slightly differently with those receptors in your nose, and then they send different signals to your brain about the two different smells.
Then if you don't know the difference, then which does it smell like? Does it...
That's a philosophical question. I don't know. That's a philosophical question. So there are lots of examples like that in nature. Some of the drugs that you guys looked up for top model, there's an R version and an S version, and only one of the two versions is the active drug. The other one doesn't work. In some rare cases, the version that doesn't work is harmful. So like, for example, thalidomide is a medication that was used to treat morning sickness. And there are two versions of it. There's the version that works, the good version, then there's the bad version, which causes birth defects. Now, the thing is, these are small differences. They cannot be separated by distillation because they don't have different boiling. Separating them in the laboratory is really, really hard. And any reaction that you do to make them, at least at that time, things have changed, would make both. But you want to separate out the bad one from the good one, right? So what happened is actually in this case, some of the bad stuff was not separated out successfully and was in with the good stuff. And so you had women who were trying to take this med for morning sickness, taking an agent that was going to cause birth defects in the baby. Go ahead.
So how do scientists make these drugs then? Do they find small amounts of the substance?
Yeah, it's so hard. So you have two options. You could either go ahead and make the mixture and then do a really good job of separating out the bad stuff from the good stuff, or sometime I'll tell you about Dr. Barry Sharpless. He's a scientist in San Diego. He actually created a reaction that will preferentially produce one. Remember, isomers are different molecules with the same chemical formula. They have different properties. We've talked about structural isomers. We've talked about enantiomers, which are stereoisomers. The last type that I want to tell you about, which is also really neat, are cis-trans isomers. Okay, these have the same connectivity. They're 4 carbons in a row. There's a double bond in the middle that literally throws a kink into things. Here's this one. I've marked those hydrogens with white. Okay? And then here's this one. You guys see that? Now you might say, well, just take this one and twist it around and then it'll be like this. Okay, let me try.
No.
You can't rotate around double bond. You can rotate around single bond, but you can't rotate around. So these are different. These are different. They're called cis-trans isomers. Okay. If I haven't blown your mind yet. Has anyone ever told you you should eat carrots because it has vitamin A and it's good for your eyes? There's some truth to that. Vitamin A is transported to the rods in the eyes, which are on the retina. Okay. That is turned into a molecule called cis-retinal. Here's cis-retinal. It's a big structure, but here's what I want you to focus on. This is a cis double bond. The 2 hydrogens are on the same side of the double bond. Okay. When it is hit with visible light, right? When your retina is hit with light, the cis gets turned into trans. You see it went from the hydrogens on the same side to hydrogens on opposite sides. And it changes the shape of the molecule. Do you see how here it had kind of a bend in it, and here it's a little more straight?
Is that how we detect?
Pardon me?
Is that how we like detect light?
That's how we see. So what happens is, after that change, it interacts differently with the other molecules around it, and then that contributes to your vision. That's one of the things that contributes to the vision.